Most people view artificial intelligence as pure digital magic floating invisibly through software code. In truth, modern AI is an absolute physical brute that requires massive mountains of customized silicon, unprecedented electrical juice, and radical thermal engineering just to compute a single sentence. To understand why the physical world is suddenly choking on AI demands, we have to look inside the microscopic architecture of modern microchips. Standard processors in your everyday computer, known as central processing units, are designed like brilliant single geniuses. They execute complex instructions one after another with unbelievable speed, handling diverse task lists smoothly. Large language models, however, do not need a single genius. They require an army of millions of basic workers performing simple math at the exact same instant. When a neural network processes information, it translates words, images, and ideas into massive tables of numbers called matrices. Training these models means multiplying billions of rows and columns repeatedly. Graphics processing units and specialized tensor cores bypass traditional step-by-step computing by packing thousands of smaller, simpler cores onto a single piece of silicon. Each core performs basic arithmetic simultaneously across huge sets of numbers. This parallel processing approach transforms a mathematical workload that would take centuries on standard microchips into a task that takes just a few days. Yet fast computation creates a brand new physical disaster, which hardware engineers call a memory wall. Calculating numbers rapidly is useless if your processor spends 90% of its time sitting idle, waiting for data to arrive from separate memory chips. Traditional computer setups send information across slow copper traces printed on a circuit board, creating a bottleneck that severely throttles performance. To solve this, modern hardware uses high-bandwidth memory. Microchip designers stack dynamic memory layers vertically right next to the computing silicon, connecting them through thousands of microscopic vertical wires running directly through the silicon itself. This reduces the physical distance data must travel from inches down to tiny fractions of a millimeter. Furthermore, when thousands of these physical chips need to work together on one massive model, standard networking cables fail completely. Systems now rely on high-speed custom interconnects, which link thousands of distinct processors together so they act as one cohesive megacomputer with almost zero communication latency. All this microscopic speed triggers a massive macro-level challenge: extreme heat and power consumption. Pushing billions of electrons through ultra-dense silicon pathways at gigahertz frequencies generates intense thermal energy. Traditional air cooling with fans hit a physical limit because air simply cannot absorb and carry away thermal energy fast enough from tightly packed server racks. Modern AI data centers are forced to use direct-to-chip liquid cooling systems, circulating specialized non-conductive fluids directly over the hot microchips to absorb heat before pumping it out of the facility. Then comes the raw electrical requirement. A single modern server rack filled with top-tier AI accelerators can consume over 100 kilowatts of power. That is equivalent to the total electricity used by dozens of average suburban homes combined at peak usage. When you multiply that by tens of thousands of server racks in a single facility, you get data centers that require gigawatts of continuous energy. This places an immense burden on modern electrical grids, which were never engineered to deliver such concentrated, uninterrupted power loads to single locations. Engineers are now forced to redesign the entire power infrastructure, building custom high-voltage substations and even pairing data centers directly with dedicated nuclear reactors and renewable energy grids. Because existing computer parts are reaching their physical boundaries, the technology industry is shifting away from general-purpose hardware toward specialized application-specific integrated circuits. Leading tech companies are now designing custom silicon tailored exclusively to execute matrix math with maximum energy efficiency. At the same time, researchers are pioneering optical interconnects that transmit data between chips using pulses of light rather than electrical currents over copper wires, cutting energy usage while boosting transmission speeds dramatically. We have officially entered an era where software breakthroughs are bound entirely by the constraints of physical engineering. The future of machine intelligence will not just be decided by writing clever algorithms, but by mastering heat dissipation, electrical grid capacity, advanced semiconductor manufacturing, and high-speed physics. If you loved getting under the hood of how physical hardware makes modern digital intelligence possible, hit that subscribe button right now. We post detailed, easy-to-understand breakdowns of the real technology shaping our world every single week. Thanks for watching, and I will see you in the next one.